see me. So I want to thank you for coming out. I was hoping to warm up coming down south, but it's really cold here. So anyway, I really appreciate you coming out on a cold night. Ron and I go back way far back. We both were professors visiting professors at the University of Colorado about 16 years ago, and maybe even 17. I think you left a year before I did.
Yeah.
But anyway, we had some really amazing conversations about some of the work that we wanted to do, and you know, some of the impact that we thought we could do. We both went to Columbia University in New York, but we didn't overlap. We were kind of passing at the time in New York, but became really good friends in Colorado, and we've kept up with each other. Done a couple of publications together, and he's just a really good friend, and has really kind of taken off. He did a really amazing book recently on the border. He was in Albuquerque, I think last year, right? And gave a great talk in Albuquerque about his work on the border. But one of the things he's been really coming along with is this sort of 3D printing realm, and has become one of the leaders in kind of looking at it futuristically and really thinking about its application in multiple materials, recyclable materials. And so I'm so sorry that he wasn't able to make it. He apologized, you know, profusely about not being able to make it, but at least we're able to produce this today. And so again, I want to thank you for coming out. And with that, I'm going to turn it over to Ron. So please help me welcome Ron virtually. It's all you, Ron.
All right. Is it possible to turn around the camera so I can see the audience?
Sure. Let me see if I can make that work.
Okay.
How's that?
Oh, wow, great. Okay. Hi, everyone.
Is everybody waving? There you go.
Yeah.
We got audience participation and everything.
Yeah. Thank you, Tim, for the introduction. Thank you, Michael, Bailey, Nicholas, all the people I didn't get to meet while I was supposed to be there. And thanks for understanding that I couldn't be there. I'm reporting to you live from the Motel 6 in Albuquerque, New Mexico. So thanks for coming. I want to begin by simply talking about the relevance of 3D printing. Maybe I'll close this down because it's going to be in the way. In the context of architecture. And just for a moment, this graph was produced by a Dutch organization a few years ago in 2015. And I hope you can see it okay, but it talks about the major innovations in 3D printing and architecture since 1996 to the present relative to material. And you can see the epicenters have been in California and parts of Europe, some parts of China. And the materials here are concrete, clay, plastic, sand, metal. I'm going to talk about a few of those innovations that we've participated in over the years. What's interesting about this graph is that it's also an exponential curve, which leads me to believe that definitely in the near future, we will be seeing architects and builders specifying materials and components that are 3D printed. Now, what we do at Emerging Objects, which is a company that I co-founded in Oakland, California, is that we invent materials for 3D printing that are affordable and strong and come from waste stream or sustainable sources. And also, we're interested in creating assembly methods that do not require specialized skills. And we like to consider that there's some relationship between the pre-industrial, the industrial, and digital craft technologies. A lot of what I'm going to show are digital craft technologies made with 3D printer. And of course, there are all the objects that are produced by the Industrial Revolution. But what do I mean by pre-industrial technologies? Primarily, the innovations that come from the handmade, and more specifically, and rooted deeply in New Mexican history, is the adobe, the mud brick. And beginning with a brick and thinking about how that as a fundamental building component can shape the future of architecture in the same way that it shaped the history of architecture to the present. This kind of came about in a book that I wrote in 2008 called Earth Architecture. I grew up on the border of New Mexico and Colorado, and I'm culturally Northern New Mexican. And this book was started by my interest in, as Tim mentioned, studying modern architecture at Columbia University in the 90s and thinking about its relationship to historic architecture, specifically architecture made out of mud, out of clay, and what that meant in terms of thinking about the future. So in this book, in the last chapter, I proposed that the future of earth and architecture must be 3D printing. And after I completed the book, I thought, well, maybe I wanted to be the person who kind of explored that. So how most architects deal with 3D printing is they have a 3D printer and they print little models of buildings. And they use them to analyze the building, think about its form, and it helps along with the design-making process in terms of models. Or this sort of thing is going on more and more in architecture, where there's attempts to 3D print concrete and concrete structures. And so I have been wondering how one 3D prints architecture in the 21st century. And for me, it surrounds notions of craft, thinking about where material come from, what are the origins of a material, and what is its history, and a notion of a print farm. And what do I mean by a print farm? That rather than thinking of one giant printer that prints an object that's in fact often smaller than itself, so the printer has to be very, very large, I like the idea of lots of printers working together to print building components. Again, building components like the very simple brick. A brick that can have its own complexity generated by the 3D printer. And in this case, this is a brick that has 4 holes. And imagine another version with 3 holes and 2 holes. But if you notice, it's symmetrical on the corners, on the edges. And so this brick can be assembled by anyone. And we sort of started off doing this, making toys and making assembly components that anyone could assemble. In this case, a structure that it doesn't matter the orientation of this brick as it fits into the wall. Here you see the 2-hole version. Over here you see a 3-hole version and a 4-hole version. But they can all be assembled very easily with 3D printed components to make a wall. And what does that mean for architecture? Well, if we decide to invest in this further, then perhaps we can build something much more complex. And rather than if we do this with one printer, what does it mean if we have 100 printers? And this is an example of a structure that we made a couple of years ago with 100 printers, a print farm of printers that were printing 54 unique parts. And why 54? Well, we realized that if you 3D print a structure and you take on the notion that complexity is free in 3D printing, which is a bit of a myth, but okay, well, a printer doesn't matter. It doesn't matter to a printer if you're printing 20 different parts. But perhaps if it doesn't matter to a printer, but it does matter to a human. And so rather than printing in this object, there are close to 3,000 components. Rather than printing 3,000 unique components, we decided to explore what's the minimum number of parts to make a doubly curved surface that would describe a dome and an opening that we could make. And we discovered that at this size, it was around 54. And what was exciting to us is that we realized those 54 had a mathematical geometry that began to define the facade and the pattern you see on the surface of this structure. So really the instructions to build this structure, which we call the Star Lounge, are embedded in the colors you see that we chose to allow us to know what parts go where. So blue goes in one particular place, red goes in another, white goes in another. And so you can assemble this into components that are much larger very quickly because you know where they go by color. And I'll let you watch this for a while. I hope this isn't too loud. But the idea being here is that you can assemble them into larger components, ship them to a site, and then have them prefabricated and then fabricate them on site, for example. So there you get a sense of how that's all put together. Now, before I continue, I do want to ask a question of the audience. Can you guys hear me okay? Is everything going smoothly over there?
Yeah. Yes.
Yeah, great. Okay. So now the printing of that Star Lounge is pretty standard 3D printing, but we decided, would we be able to take control of the coding language that could print objects? And what does it mean if we could? So we started working on this project called Gcode PLA. And what we're doing here is we're weaving the plastic back and forth to decide where we want thickness and where we want thinness. So rather than describing that and leaving that up to the generic slicer, we created our own slicer that allows us to make these determinations. And the outcome is really interesting because we can embed thickness and thinness, in other words, structural areas or areas of more translucency or less translucency, or patterns and geometries into the surface, and we have total control of it. And so here are some of the outcomes of those experiments in Gcode and bioplastic. But plastic wasn't completely and entirely our main interest. We were always using corn-based bioplastic, but we did find problematics with what does it mean to print plastics when at the same time we're reading news about Texas-sized plastic islands in the middle of the ocean and recognizing that it's one of the biggest pollutants on the planet. So what are other materials that we might be able to use, and can we invent those materials? And so this story of invention also starts just in our house on the kitchen table, and we began to look around, what are the waste products that surround us every day? And one of them, of course, is coffee. All the coffee grounds that one throws away every day in their kitchen, and what could you do with it? So we developed a 3D printed material out of waste coffee grinds, and we printed a series of coffee cups just to test it out. So these are coffee cups made out of 3D printed coffee. And this is a 3D printed teaspoon made out of sugar. And so you could decide how much sugar you want in your coffee cup by putting 1 teaspoon in it. And it happens to be that that teaspoon is exactly the volume of a teaspoon as well. So that's a perfect teaspoon of coffee as a teaspoon. So you can have half a teaspoon or a quarter teaspoon or a teaspoon and a half, depending on how much sugar you like in your coffee. But it doesn't make any sense to make a teaspoon out of sugar. So we wondered if we could make a material out of tea. And so these are the 3D printed teaspoons that are exactly the volume of a teaspoon, or a teaspoon and a half, or half a teaspoon, depending on how much tea you like in your tea, I guess. But if you have a teaspoon made out of tea, then you need a teacup. And these are the 3D printed teacups, 3D printed out of tea. And this is the teacups and the coffee cups made out of tea and coffee with the sugar spoons. But if you have a teaspoon and a teacup, then you need a teapot. And what teapot would we use? Well, we looked at the history of computer-aided graphics and design. And one of the very first objects ever translated into the computer and rendered was this teapot called the Newell teapot, or the Utah teapot. This research happened at the University of Utah. And this technology went on to create companies like Pixar, for example. So you'll see in every Pixar movie, this Utah teapot will appear in some scene, like Woody in Toy Story will be pouring from the Utah teapot. So we've now liberated the Utah teapot from the computer rendering back into the real world. And this is the Utah teapot 3D printed out of tea. And this is what we call the Utah tea set. So what other materials are waste materials that are locally available? Well, I live in the Bay Area in California, and in nearby Sonoma County, there's an enormous problem with the amount of grape skins that are left over as waste as a product of producing wine. And sometimes they're dried and used as fertilizer. People have tried to use them as animal feed and even tried to package them into small fancy bags and sell them to humans to make cookies and things like that. And so we went and gathered some of this grape skins, and a company dried them and powdered them, and we turned them into a 3D printable material. And this is 3D printed Chardonnay goblets made out of Chardonnay grape skins. In addition to the Chardonnay goblets, we 3D printed this this ice bucket made out of Chardonnay for Design Miami a couple of years ago with the designer Andrew Cudless. And we participated in the making of these tables as well, which use this Gcode PLA technology. So working with organic materials like grapeskin has allowed us to think about other organic materials as well, like paper, which comes from wood pulp. And so with my students, we did some research looking at taking ground newsprint and turning newspaper, which is an enormous landfill problem, into a 3D printable material. And so these are some of the examples of the objects that we printed, nothing so fancy, but that led us to be able to explore a material that is much more widely available, which is wood. And in the United States alone, there's about 7 million tons of wood waste thrown away every year from the construction industry. So fundamentally, wood is a subtractive technology. You start with a tree and you chop it into smaller and smaller pieces until all you're left are with the waste bits that can be used, often in the form of sawdust. And so could we take that subtractive industry and turn it into an additive industry? And so this was our speculation. So we began to test different kinds of sawdust and developed a wood material made from nearly 70% sawdust. And so this is our 3D printed wood material. We've been able to strengthen it by inserting fibers into it to increase its tensile strength. And what's interesting about this very unnatural synthetic wood is that the process of the 3D printer actually begins to introduce a kind of new nature to it. And you can see the grains of the wood that are not part of the growth of the rings of the tree, but in fact, they're part of the growth of the object through the lamination process in the 3D printer. We can print it in ways that do things that wood doesn't do normally, take on shapes or thinnesses that promote translucency and transparency. And we've worked with various kinds of woods, softwoods, hardwoods, pines, even nut shells, for example. And so walnut shells, pecan shells. But we're always thinking about it from this fundamental component, the brick or the tile, and what it means to take those tiles and aggregate them to begin to think about the making of facades or walls or screens or partitions in the context of architecture with detail and materiality. And again, always recognizing where does the material come from and what is its life trajectory and where does it go afterwards. And so we're always thinking about these issues when we're developing these materials and the stories and the legacies behind them. Like, for example, in the story of rubber. In the United States, there are about 300 million tires thrown away each year. Fortunately, in the United States, about 80% of those tires are recycled. But this is an aerial photograph of the largest tire landfill in the world in Kuwait, where 0% of tires are recycled. And so you can imagine the number of cars in the United States versus the number of cars in Kuwait, for example, and what kind of impact that has on the landscape. Well, we began a few years ago to work with a company who recycles tires and grounds them into a fine powder in order to find a market for them. And their market has chiefly been in making an additive to asphalt road production. But they asked us if we could take this powder and invent a 3D printable material with it. And so with the knowledge that we had in doing this so far, and it's interesting how they make this. In fact, they cryogenically freeze the tires using liquid nitrogen until they're frozen solid, and then they can smash them into the powder. And so here are a few objects that we have printed to date. They're very experimental and kind of, we haven't produced a lot of this because it's very labor intensive. This particular one called the rubber poof is now part of the permanent collection at the San Francisco Museum of Modern Art. So other materials in our context and our landscape are materials such as salt. And this is a material that's widely available in the South Bay of the San Francisco Bay Area. In the trajectory of objects that we make, of course, if we're making coffee cups and teacups and Chardonnay goblets, we made 3D printed salt shakers, which doesn't make a whole lot of sense. But what makes sense to us is thinking about how this landscape, which produces thousands of tons of salt each year, might contribute to the making of artifacts and objects and architectural components. So if you ever fly into the airports in San Francisco, you'll fly over this part of the South Bay where these salt crystallization ponds are. And they turn different colors throughout the year because of the microorganisms that live in this stalinous, warm soup that is basically a brine. And once this dries, it produces up to 4 to 6 inches of salt each year through sun and wind evaporation. And then it's harvested into these piles that you can see. So could we take that salt, which is sold by the trainload, so it's extremely inexpensive and very sustainable to produce, and turn it into a 3D printable material? Well, this is the material that we've been developing for several years now. It's translucent, it has this beauty of salt, it has this history and legacy of coming from the sea, of being something that's consumable. There's a long history of producing architecture out of salt in South America and in the Mediterranean and Africa. And so maybe this is a new way to produce architecture. And because it was inexpensive, we began to realize that we could aggregate it together and imagine the possibilities of what it meant to produce a salt architecture, a salt building, or salt wall components. We did this one with the designer Tom Falders to think about how we might produce a large-scale salt building. And this was a model that we produced for him for the Frack Center exhibit. So the largest project that we took on ourselves was inspired by a newspaper article where we discovered that the company that owned many of these crystallization ponds also owned adjacent property, and they were going to develop over houses for over 40,000 people in the coming years from the land next to the crystallization ponds. And so we wondered if we could think about what it meant to be inspired and create an architecture from the landscape to participate in that construction project. Purely theoretical. But we were inspired by the Inuit igloo as a kind of structure that is produced from the landscape. And so we took on this project that we called the Salt Igloo. And we called it the Salt Igloo because it was made of salt igloo. You guys laugh? This would be funny there, right? You get this joke. Okay. And so we looked at traditional salt crystallization processes around the world. We were actually invited to China to think about this also in a component of architecture there. So this began to fund the research further. And if, for example, the Star Lounge was a project that looked at file management in terms of research, the Salt Igloo was to think about how quickly could we take advantage of a 3D printer to produce what was fundamentally like a lightweight salt tent. So the Salt Igloo was like a tent, really, that had very thin tiles so that we can print many at one time. Every tile was different in this case, and here are some examples of those salt tiles that were then aggregated along a surface and clipped together and attached to lightweight aluminum rods. And so this is the Salt Igloo being constructed in our studio. You can see the interior, you can see the lightweight aluminum rods holding this and flexing it in tension. And a similar principle, it was made in larger panels and could be stacked very quickly. And this project has been exhibited in a lot of places, so I'm still surprised by its ability to be packed away and stored and shipped and erected quite quickly by people who are unfamiliar with this process in many parts of the world. That photo is taken in Canada. But our aspirations are always architecture and thinking about how these might be applied in architectural scenarios. I mentioned the project in Beijing where this was meant to be implemented, the idea being that all of the private areas of this house in a development outside of Beijing would be clad in this salt material. So the bedrooms, the bathrooms, the pool house would all be made out of salt, and the rest would take on a very traditional construction system out of concrete, which is what they were very good at. And so our aspirations for this, or our belief, is that 3D printing isn't going to be the end-all be-all technology that comes around and replaces everything, but that like Adobe, for example, or and being supplanted by other materials, that they would work in conjunction. And what I mean by that, you can see in the architecture and the history of New Mexico that there were adobe buildings with earthen floors and earthen roofs. And then with the introduction of the railroad and the sawmill, you suddenly saw corrugated metal roofs and pitched roofs that were made out of sawmilled lumber. And so I think the same kind of trajectory in history will happen in the future of architecture that is made through 3D printing processes. So we also began to explore the facade of this building, which was not to be 3D printed in salt, but using another local material. And the intention of the facade was that it would define various views and allow light in particular ways throughout the day. And the way that we explored this was thinking about how we could 3D print this out of sand. And so sand is a very ubiquitous material around the world. We wondered how we could employ sand into the 3D printing of this facade. And so we produced these large-scale 3D printed sand blocks that were the facade samples for this project. And again, they were defining views and light in very particular ways, and really meant to maximize the way a 3D printer works and how you could aggregate it. I showed that very first slide of the bricks with the 2 holes and the 3 holes and 4 holes. So we took that same idea in principle and 3D printed out of sand, with the idea that these could be printed, shipped to the site, and installed at the discretion of the contractor in any direction, and the pattern would be formed by that group that did the assembly. Other experiments in sand are experiments about sound attenuation, ways to print walls that can absorb sound and deflect sound, because the sand components are really massive. They're thick and heavy, and they're really like stone. And when we discovered that they were so massive and heavy, we wondered if we could do a project that responded to our own local seismic problems in the Bay Area. And so we embarked on this project called the Quake Column. And what the Quake Column does is it looks back to the traditions of Incan ashlar masonry, where stones were fit together in such a way that they could actually resist seismic loads, because the load doesn't find a single trajectory to move through the wall like it would in a regularly coursed brick masonry wall, where the load can find its way through the mortar and just bust it apart. But instead, the load has to move through the various sizes of bricks and the various joinery, and actually can shift and settle. And so that's one reason that Incan architecture has lasted so long, because it has this capacity for flexibility, even though it's so massive. And so could we learn from that and print a series of blocks that also interlocked and interacted with each other, and that had a bit of intelligence built into them based on how one would assemble them. So the instructions and even a handle was designed into each block so the workman could carry them and stack them in place. So here's how tightly they were able to fit together. And you can see them being joined there. You can see the instructions so you know where they go in space. You can kind of see the handle. It gives just enough finger grip so you can pick it up and put it in place. And so that's the Quake Column, we call it, weighing nearly a ton. There's this really massive stone structure. And as always, the ground beneath our feet has been the primary interest, and really has driven us to do everything that we've done in 3D printing. Printing with clay. What is the future of clay architecture, of Adobe architecture? And so speculating, what also, sort of situating questions about what does it mean to produce this work, and what meaning will it have in the future, not only the past. So we can think about clay being a now 30,000-year-old tradition that's going to last much, much longer, that the objects we produce today will last hundreds of thousands of years if we make them out of ceramic. And what does that mean for a 21st century ceramic production? So this work is some of the oldest work, thinking about how we could print directly with clay itself. And the early experiments were very refined, very thin, but we also began to explore how we could fire them in the kiln, and you turn them into ceramics, think about glazing, and ask questions about what would we make with this? Would we make bricks that could insert into traditional masonry systems, but maybe they held plants or water? Maybe we could make more complex forms out of ceramic that had air pockets in them and they could be insulative. Or in the case of one project that we worked on, could we begin to combine traditional technologies together to make a brick that actually performed in a way that worked as a passive cooling system? So this particular cooling system has been around for hundreds, if not thousands of years, and it's comprised of a porous ceramic vessel that's filled with water and placed in a window in an arid climate. It's used in India, it's used in the Mediterranean. You can find it in use today still in Spain, parts of Africa. And so the ceramic jar is filled with water, and when the warm breeze passes over it, it humidifies the air and brings that into the space. And humidified air cools the temperature in an arid climate. And so this is essentially the idea of the swamp cooler today, where you're blowing in humidified air into a space to drop the temperature. But this is a much more passive technology. So could we combine all that into one building component through 3D printing? The idea being that we could create two levels of porosity. One, a micro porosity defined by the 3D printing process that can absorb water like a sponge into the porous brick. And a second level of porosity that allows warm, dry air to pass through the brick, taking on the evaporated moisture in the brick itself and bringing cool, moist air into the building. And so this is the challenge, and this was what we called the cool brick. The cool brick does just that, and it's really amazing how the capillary action pulls the water into the brick itself. It's like a sponge, and you cannot shake that water out of it. The relief that you see keeps the wall in shade, and the matrix that makes the porosity for air to pass through also serves a double function, in that it holds each brick together with a traditional mortar much more firmly than in a flat brick. So there's really no tensile strength in a flat brick. You can just move it away. But in this case, it creates a strong bond because the mortar weaves into the meshwork itself. So here's our cool brick wall prototype that we produced. So our other experiments in clay have surrounded thinking about how we introduce the concepts of the Gcode PLA in plastic into the Gcode CLAY, the Gcode clay, and thinking about how that dance of the machine could begin to produce interesting objects that you wouldn't necessarily make with your hands. So 2.5 years ago, we embarked on a body of research that has now turned into like a movement in the ceramics world, and really exciting for us to think that we were kind of there when it started, to produce objects like this or objects like this, not knowing what the outcome was, either as a technological movement in ceramics or what use they would have. You know, to make objects like this, we don't know the use for these, but it's kind of pure research in a way. They're beautiful, they're interesting, they're fascinating, they have this amazing texture, but what can they do? We did not know, and we did not care. We were just fascinated by playing with the robot and just saving every single experiment that we made, and really began to push what the possibilities were of taking on texture and surface, opening, porosity. And after about 2 months of just printing nonstop, we saved every single object we made and fired them and had an exhibit that looked at all these varying textures that we produced. It really became a textural process that was more like knitting or stitching or textile design. You can see here that really expands not only the nature of what you can do with clay, but even the linear deposition process of 3D printing itself, which at that time had been basically a series of striated layers stacked on top of each other. And it opened that wide up to think about the plasticity of clay, the gravity, And even, I may dare say, the hand, how this notion of the hand produces a kind of unique quality through air. We allowed the machine to take on this same responsibility of producing air rather than perfection, and wondering how these might contribute to the making of architectural skins, for example. And these were a series of experiments we did thinking about 3D printed ceramic cladding systems held entirely together with 3D printed joinery that might become building skins, and what it meant for, let's say, a surface that would micro shade and become cool because components of the, or the surface area wasn't entirely in the sun but in shade, what it might mean for assembly and joinery. And then, of course, the material that everyone is thinking about in architecture is cement. And rather than thinking about 3D printing wet concrete, which is very hard to stack, we decided to use our process to use very little water and a dried powder cement, where you can make objects that are very complex without any formwork that would be impossible to make even with formwork, and what it meant for the future of architecture as cladding systems that made out of cement but are thin enough to be translucent, for example, but that are also lightweight, but appear to be heavy and dense. So, for example, this object, which is about 3 feet across, is held together with paper clips. So objects could be made that are very complex, that would be difficult to mold or expensive to mold, and be put together very quickly using simple assembly methods. One example of this is a project that we created, and was one of our first outdoor projects, a bench designed to watch the America's Cup, which was taking place that year in the San Francisco Bay, intended to be at the end of one of these piers, the pier in the middle there. And so we designed this seat to be based on a sea slug that was recently discovered off the coast of California. And we loved the beautiful back of this sea slug and wondered if we could make a pattern like that that was logical and one could sit on, and how one would make it easily and design it. So we used a very traditional Japanese textile pattern system called karakutsa, where we designed one tile and we repeated it and rotated it randomly across a surface. And what this does is it makes a non-repeating pattern. So you can't find a single pattern that repeats itself within the system when it's deployed along a surface. So this, on the upper left-hand corner, is the design of the seat, focusing views in and out into the bay, and a point distribution system that allows us to make as many parts as we can that would fit within the constraints of our printer. And so here are all those blocks printed out and laid flat, ready to be assembled together. They have a joinery system built into them. Here they are curing in our studio. You can see the joinery holes in some of the blocks. Here it's being assembled. And here's the seat put together that we call the seat slug. So this really opened our minds to the possibility of what it meant to work this way digitally through creating a rendering, and this is the rendering, and moving directly from the rendering and that same information into the fabrication, going from visualization and design into making and deploying and testing. So whereas architects traditionally have used 3D printers to make models, to analyze and make decisions about the form, the look and feel, we're still doing that, but with the understanding that now we can take that same information and 3D print the structure directly from that. This is one of the largest things that we've printed to date, a small pavilion that we call Bloom. And it has this beautiful flowered pattern on the surface. It's made of iron oxide-free cement, which removing the iron oxide from cement basically makes it whiter, and it's used a lot in swimming pools. And so we use that particular material. But every one of our experiments is an experiment in thinking about how we could design more rapidly for the printers. Because when you have farm printers, you want them working all the time and never resting. And so this process was a process where we simply instructed the surface of this structure to open or close based on the white or black value from this image. And then we mapped it to the surface of that object, and this is the result of this very figural result of openings and areas that were more or less closed to create not only the pattern, but to create a kind of phenomena and experience in the structure. Because of the lightweight properties of this material that we invented, and also because of its strength, we're able to achieve very thin parts, especially at the top. So the bottom is approximately 6 inches thick, or I should say deep, and the top is 1.5 inches, if I remember correctly. And it has this doubly curved surface that makes it very rigid all the way around. You can see it there. And the inside has this structural set of ribs, and this is why I talk about the depth versus the surface. So the surface is this very thin open and close area with these ribs, so it allows light in really beautiful and remarkable ways. You can see our concrete building in the background and the 21st century concrete in the foreground. And each of these components was designed to be assembled together into larger components and then shipped to site and installed. And so after it was constructed for the first time in our laboratory, we then took it right outside and installed it in the courtyard and had kind of a party around it. And it was important to be able to do this because the project was sponsored by a Thai concrete company. And so the project actually had to go to Thailand right after this event that celebrated its construction. And so this is why we broke it down into smaller pieces so it could be assembled quickly. And it's been put up and, or say, erected and dismantled many times throughout its history. You can see how quickly it's put together, and just 1 or 2 people can actually pick up one of these panels and carry it away. And it has a compressive strength stronger than concrete itself. One of my colleagues said to me, well, it's amazing how you always look back at tradition and history around the world based on places you traveled. And I actually didn't realize when he said that it looks like those West African structures that you visited as a student when you were studying architecture. And I realized that he was right, that relationship between us looking forward the future of architecture is simultaneously looking back at the traditions and the beauty of vernacular architecture itself. So many people ask us, do you ever bring this all together? You're printing only in cement or only in Chardonnay or only in wood. Are there examples where you begin to hybridize this? And so we're beginning to do this in a number of ways. One is simply beginning to mix these materials on surfaces. And so walls that consider the use of sawdust and cement and Chardonnay, but also beginning to think about how in one object we can make a gradient from the top of this material, which is 100% Chardonnay, to the bottom of this material, which is 100% Portland cement. And to think about what that means. What does that mean to make an object that is both biological and geological? If you consider Portland cement to be geological, one could argue that it's also biological as well, because it comes from fossilized seashells that are millions of years old. So what does it mean for the history of object making? And what does it mean for the future of object making when we move through this threshold moment between thinking about the archaeology of an object and the future anthropology of the object? What does it mean to make an object that is 100% Portland cement at the bottom and 100% curry at the top? I don't know the answer to these questions, but it's something that we can do, and it's something that we're exploring, because I think when we leave questions open-ended like this, it's much more in line with science. And I think science and art share this responsibility of not defining use, but thinking about what's interesting. Design has the responsibility of thinking about its use. Of course, engineering shares that responsibility as well. But I think what the beauty of design is that it moves between art and science and engineering, that it both has to be beautiful and interesting and useful. And so how do we begin to bring these into some utility? We don't know yet, but I'll say that one other way that we brought these materials together is that I was in El Paso at a time when our current president announced that there were a lot of bad hombres at the border. And I thought, oh, that's really funny. They're bad hombres at the border. He didn't say they're bad hombres at the border. They're bad hombres. And hombres are gradients between dark and light. And so we produced this series of objects that we call bad hombres. And they're ceramic vessels that have both clay from the Republican state of Georgia and clay from the Democratic state of California, both dark and light clays that weave together. And in a single object, you can see those gradients and you can see the distinctions. And so I thought our president was very astute to recognize the kinds of gradients and distinctions that exist in that landscape. So other ways we're beginning to bring this together is to think about how we could take clays directly from site and begin to 3D print them. I'll say again, inspired by our president, because the main idea of this project about hombres, I mean, the optimal goal would be that we would take clay from Mexico and clay from the United States to produce these objects. And so after we made them, we said, well, let's go out on site and begin to dig up the clays themselves and refine those clays and put them in the 3D printer. So what you see on the screen right now is a gradient of the complexions of clays based on various sites that we pulled in Juarez and El Paso. And so it's exciting to us to think about all this variation, to think about the history of pottery that has existed in the border region between Juarez and El Paso for centuries, before there was even a Juarez or El Paso or distinction between the two. And even super exciting for us is sample C. And I don't know how many of you have been to Juarez, but there's a very amazing building called Casa de Adobe. Casa de Adobe is pretty much next to the site where Border Monument 1 exists. And that's also the site where the Rio Grande becomes the border between the United States and Mexico. Before that, it's a land border between California and El Paso. And so it's at that one particular site, which is also the site of the beginning of the Mexican Revolution, where this very white clay is. And so it's kind of exciting to see that this gradient exists in colors and browns, and then the white that exists at that moment where Chihuahua and Texas and New Mexico come together. And so we're working on this project now called Future Ruins, which is going to create a series of pottery objects that explores the clays in both these contexts. And so firing these clays is pretty exciting because color really comes from the firing itself and the objects that are created. So that's going to open at the Rubin Center at UTEP in January, if you're able to come down, because it's not that far. This idea of exploring clays came from a project that we did in collaboration with Google Arts and Culture. They were working on a project at the Museum of Mumbai that celebrated the 10,000 years of pottery in India. And they asked us if we would 3D print a series of objects for them and ship them to the exhibit based on a software application that they had made for the exhibit, where anybody could write a word that they thought would be the most important word to consider in 100 years, and then would be placed on a piece of virtual pottery and later physical pottery. And so this was the exhibition where someone could go in and write, and then it would appear on a pot. And they asked us if we would take those top 10 words and print them on pieces of pottery and then send them to the exhibit. And we said, no, we have to go to India and print it with Indian soil. So, because this is an exhibit that's going to happen in 100 years in Mumbai. And so it's important that it comes from Indian clay. And so we were brought to India. We worked with this person here, Panajit, who's the most important potter in India, which was an amazing experience. That's him in front, that's me in the back. And we developed this set of pottery based on traditional Indian pottery, but also inscribing the words that were written in this exhibition on the pots themselves in 3 languages, English and Hindi. And you can see the English and Hindi here, book, plastic. I don't know if you can read those. Mobile phone. This is both book and book in English and Hindi. If you look sideways, if anyone can read Hindi in the audience, or English for that matter. Car. These were some of the words that were put. 3D printer eventually became one of the top 10 words after 10,000 students came through our workshop. So even though we detoured for a moment into pottery, there has always been this interesting relationship between pottery and architecture, because both seek the making of space through the making of an object. And so our aspirations continue to be architectural, but we realized that we needed to take one more step of control, moving into the creation of software and hardware. So in this past year, we began to develop a piece of software. The primary role of this piece of software is to think about how we can design buildings at a larger scale using a software. But the offshoot of that exploration is that the software allows ourselves and anyone to engage the software to produce the kind of objects that we have been making over the past 3 years. And so this software is now commercially available. We've commercialized it, and there are about 20 high schools and colleges and universities around the country that are using it since we launched it back in, well, 3 months ago. And so it runs in the cloud, and you can download these objects and print them directly with a 3D printer. But what we also did is we embarked on the design of a 3D printer itself. And we worked with a 3D printer manufacturer who manufactures a ceramic 3D printer with the goal of 3D printing a machine that can print objects larger than itself. And the outcome of that was a machine that could also print a number of objects at once. So not only one object, but it can move all the way around itself 360 degrees and print many objects, or print one object very large all around itself. Essentially, it could actually encapsulate itself in the print itself and trap itself in it. And so this machine has also been commercialized in the past year. And this is the commercial version of the machine, but it opened up new questions and problems. So taking on hardware and software was one thing, but also material delivery. And what does it mean to push massive amounts of clay through a machine in order to print architecture? Because our goal is to print Adobe. And so this is about 1.5 years ago when we finally kind of got it working. That's a human 3D printer that you just saw there. But about 4 months ago, this is where we were. And we finally were able to develop a system where we could push massive amounts of clay and straw and sand through the machine and print objects. And so you can see this first early experiments. And here's some other videos of that in action. So just 2 weeks ago, we headed down to El Paso. We invited students from Texas Tech and the University of Texas El Paso to help us mix lots of mud and straw and sand. And we began to put our 3D printer to task, 3D printing Adobe on the border in Texas, in a landscape where now technology and material and tradition and the future were all coming together at this important site on a mesa overlooking Juarez. So these are some of our very first experiments just 2 weeks ago in El Paso, printing these 3D printed Adobe structures, thinking about the texture and the materiality and the surface. And we only had 3 days, so we had to move quite quickly. That's my son there holding a blowtorch so we can make the Adobe dry a little faster so it can stand up. Here's the machine, a really small, delicate machine that you can actually put over your shoulder and carry to the site, 3D printing these structures that are much larger than themselves. And because we only had 3 days, we couldn't go up very high because you have to let Adobe thicken. But we began to also explore those same kind of textures and qualities that we were exploring with the pottery, scaling up these ideas of how the software and the hardware and the material and gravity can all interact to create a new kind of technological and historical aesthetic. That's on the mess overlooking Juarez there in the background, and these new Adobe structures of the 21st century. So this is sort of where we are. This kind of encapsulates our ideas and our ethos in our lab and studio and company. That on the left-hand side is a Musgum hut, a traditional hut that is replastered every year, and the ornament that you see on the surface also serves as a permanent scaffolding. And what you see on the right is a set of experiments. It's a dance with clay and gravity, and we don't know what it's for, but we like to think that maybe we would find out what it's for by pursuing these kind of experiments. So one thing we did recently is we took the Gcode PLA and traditional mud plastering methods, and we created a structure that's kind of like a jacal. I don't know if everyone in the audience knows what a jacal is, but in New Mexico, a jacal is a structure that's made out of woven branches and plastered with mud. They're some of the earliest structures that were built in New Mexico and southern Colorado before one would build an Adobe structure, because they were much faster to build. But in this case, we have the corn-based bioplastics serving as a replacement for the branches, and we have local soil from the Limoges clay mines in Limoges, France, where we built this installation. So here you can see us taking on this task of plastering this structure, which is very lightweight. It has a pattern defined into it that gives it kind of half the rigidity, but the clay itself gives it the remainder of the rigidity once the clay dries. So we call this the jacal digital, the digital jacal. It was a family affair. Our son rolled all the clay so we could plaster it. So how else can this technology be used? Well, we've been working on a project for this bird called Cassin's auklet off the coast of California on this island called Año Nuevo. And these birds have been increasingly losing their habitat due to sea level rise. And so scientists have been working for a number of years to create artificial nests, and they found ceramic works very well for their nests. However, the best ceramic artists whom we're collaborating with take a very long time to construct these nests, which require a degree of complexity to them. You can see the opening, kind of the front door of the nest, and you move around the shell, and in the center there is where these birds lay their eggs. But then the chicks are so annoying that the birds need to go around the wall and like hang out away from the chicks while they're squawking and quacking and everything. And so it has to kind of have this complex inner core for the nest, because this is what they'd find naturally in the rocks. And so the nest also has to support the load of a sea lion. So ceramic works very well, and we created this kind of dome structure. But also we're using this Gcode clay process by controlling the machine to create small openings for ventilation and to create a micro shading so it keeps the nest cool in the sun. And there you can see the ventilation holes made by the guiding the printer. It's a double wall system, so it's ventilated and it's insulated, and there's a layer that's shaded from the sun. That's the first version that we put out last year. We took them out on rafts to Año Nuevo, and they were installed. And so we're going to find out the data just in the next few weeks of how these nests performed. And this is this year's version, which we're taking out very soon. They're in the kiln right now, and they have these raven-proof lids now. So rather than scientists sticking their arms into that long tunnel that you saw popping out before, now they can just lift off a lid. They couldn't do this very easily before because the ravens would figure it out, but now we've designed these lids. So we'll see how they perform over the next year, but it looks pretty promising. A number of scientists have come into our lab and to ask us questions, and one asked us, based on all the materials they saw us printing, could you print calcium carbonate? And these are scientists studying coral reef degradation. And so we took the challenge to see if we could print calcium carbonate, not because coral necessarily like to establish themselves on calcium carbonate. Coral actually produce and secrete calcium carbonate, but to demonstrate that if we produced a series of calcium carbonate objects, and these ones were forms that were scanned from coral reef in Australia, that scientists could use these as teaching tools to demonstrate how higher acidity levels in the ocean due to pollution and climate change disintegrate calcium carbonate. And so they use these as teaching tools, these calcium carbonate objects. But they saw all of these ceramic vessels with all these loops, and they said, wow, that looks like great coral habitat. And coral, in fact, love to lodge themselves on ceramic in our lab test. And so we began to collaborate with scientists to design a series of 3D printed ceramic coral reef seed pods to be tested in oceans this year. And we've produced over 4,000 of these seed pods, and they're being tested right now all around the world, in Curacao and Baja California, Australia. These are some of the sites where these are being deployed, and using different processes, powder-based processes and extrusion processes. And the results are already showing that they are working, in fact, as well or better than many of the experiments they used in previous years. So it's pretty promising. And if things go well, we'll be producing tens, if not hundreds of thousands of these objects using 3D printing over the next several years. One of the final ways that we're bringing this all together is also to make not only animal habitats, but human habitats. And so the next and last project I'm going to show you is called the Cabin of 3D Printed Curiosities. And this is a project that combines many of the techniques that I've shown you tonight, many of the material systems and many of our ideas put together in a single cabin. The exterior of this cabin is clad with over 4,000 ceramic panels. And each of these, I actually call them tiles. And each of the tiles is actually the same tile, 3D printed over and over. But in fact, in the way that we design the tile, the printer creates an error at the edge of the tile. So in fact, every tile is unique, and it has this distinctive kind of direction to the tile itself. And so we also used recycled clay for those tiles, making every color of the tile different as well. The front facade of the cabin is made out of Chardonnay grape skin, 3D printed sawdust, iron oxide free cement, normal Portland cement, and houses a number of succulents and air plants that really thrive in the California climate. And you can see here, and so this cabin, in fact, is now approaching, it's over a year old now, and it's still performing well. So it's really a case study structure about how these materials will work and perform over time in the weather. The house is it's a accessory dwelling unit in the backyard of a secluded garden. And it's a response to the housing emergency in the San Francisco Bay Area. I don't know if all of you are aware that San Francisco and the Bay Area are now the most expensive place to live in the country. And because of this, the East Bay and San Francisco have relaxed their zoning policies. So now you can build up to 1,200 square feet in the East Bay without an architect or going before the Planning Commission. And so this opens up the possibility for research and experimentation. So we took this on as an opportunity to really explore these ideas. The interior is a 3D printed bioplastic made out of corn. It's backlit and translucent, so we can set the mood and tone of the interior of this cabin throughout the day or the night. The panels are, you could think about them like pressed tin, but in fact, every single one of them is different. So again, these ideas of molding and formwork are called into question, because you wouldn't need, in this case, several hundred different molds, but the 3D printer can take on the challenge of 3D printing this kind of complexity and difference in the interior panels. And even the furniture, or much of the furniture, is 3D printed. And so the coffee tables, the chairs, the lighting are all experiments in 3D printing and how that could be explored in a domestic environment. So here you see a photograph of the cabin at night with the more white light, so it appears like it's daylight, but a beautiful soft light. Here you can see as the evening goes on, a bed appears from the couch. The lights are toned down to a blue that begins to put you to sleep. And this is the Cabin of Curiosities. Thank you all very much. You can learn more about our work in a book we just produced called Printing Architecture. Thank you.
Do you think you could take a few questions?
Yes, I'm happy to take questions.
Is there any questions? Yes.
What are the different pieces that keep this stuff glued together?
Did you hear that? So what are the different adhesives that keep this glued together?
Well, in all of our materials that we invent, we use we use like natural materials and non-toxic materials and low VOC polymers for the waterproofing component of it. So a lot of our materials, like let's say the salt or the Chardonnay, these are completely edible after they come out of the printer. And in fact, if you could eat wood, which I guess you can, that would be edible as well. So it's very non-toxic. Even the rubber, we often coat the materials with a low VOC polymer, and this infiltrates the porous objects themselves. So it gives it a high degree of strength. But in fact, that polymer is made out of waste stream material as well. So the polymer was invented by some colleagues at the University of California Berkeley who patented this material process as well, which is a polymer made from sawdust and bamboo, recycled sawdust and bamboo. So the materials, we always have this ethos that we're using sustainable materials, locally sourced materials, but that all our adhesives, these are all very natural agricultural waste products, for example.
Any other questions? Right. Okay, Michael's got one.
So
Okay.
in the ceramic printing, it looked like, you know, you had some hopper-based things, and in other ones it looked like it had like a plunger pushing down through it. What is, and then, you know, as you grew in scale all the way up to the Adobe, it's kind of an interesting process. But we have such a rich ceramic heritage here in history in Silver City from the Hombres culture. If you could tell us a little bit more about how that kind of evolved.
Right. So I can't take any credit for the design of the smaller scale ceramic machines. I had been following someone on Google for a number of years because I had tried to build my own ceramic machines, but not with very much success, because most of the printers that print a ceramic paste or a slip. And so you can't make very large objects. But this one guy was using compression and pushing full body clay through the machine. I thought, well, this is the way to do this. And so I bought one of his first machines. In fact, I bought a couple of them, and that's how we produced all those objects very early on. And we had a very synergistic relationship because I had produced a number of objects that were really exciting and new in the ceramics world, which I didn't realize. I wasn't really aware of what was going on in the ceramics world. And that began, in turn, for him, allowed him to sell lots of machines. So his company really took off. So we collaborated back and forth, and all of these experiments that I would do would contribute, again, to his business to the extent that I felt comfortable enough saying, hey, I have an idea for a big 3D printer. And I did that sketch that I showed of just this machine spinning around itself. And he said, let's do it. And so we had been collaborating, working on that for a year and a half and got to test it out. But we had produced some very large extrusion devices with enormous amounts of pressure to push it through hoses. And there's lots of like physical reality problems with that. We had plenty of exploding hoses and clay flying all over the place. But when we began to think about it in terms of Adobe, we were able to look at equipment and machinery that were already doing this sort of thing, moving, pushing, pumping concrete slurries, mud, food products. And so we bought one of these machines, attached it to our 3D printer, and again, for the first time, tested it out in the field last week with sand and salt. So we still have work to do. It didn't work perfectly, but I think there's a real opportunity, and we're exploring that with the University of Texas, El Paso, and their students in ceramics to think about how we begin to combine these traditions of pottery and the current technologies together in one place using earthenwares. And so we are pretty excited about that relationship that we made with the Rubin Center down there and the work that we're doing in collaboration with their professors and their students.
I have one question, Ron, and then I think everybody's probably ready for some dinner.
Yeah.
In terms of, with the new makerspace here, I think the emergence of 3D printing is sort of a global trend. And one of the things that is kind of emerging is, commerce that comes out of 3D printing. Where do you see it happening, and where do you see it going in terms of, sort of micro commerces coming out of different areas around the world?
Yeah, that's a good question. What has been the trend for a number of years is that the things that made money, the things that sold, were the printers themselves. And there wasn't a lot of concern for what came out of the printer, right? So big businesses were started that were 3D printing companies. But can we think of companies that were made by using 3D printing technology? Probably not many that we can mention offhand, but now we're at this point where almost every hearing aid produced in the United States is 3D printed. And people are beginning to print engine components and automobile components using 3D printing. I think it's still very open-ended. I don't know where that will be. There's one thing about ceramics that I will say that's exciting, is that it's very fast, very inexpensive, and you're producing an object that is going to last 100,000 years, and it can be useful, it can have a utility. And I think there is a real opportunity there in 3D printed ceramics to begin these kind of, how did you call it, microeconomy, like a small business. I think that's possible, because I think that's one place. But I also think it's open-ended, because of the creativity of designers and artists is infinite. And so we're yet to see where it's going to go. And I'm excited to see where it goes, but it demands everyone to get into that makerspace and use it and really explore what's possible, and not to be afraid and to experiment.
Right. They have a clay fest here, right? You're going to have to make it.
I didn't know they had a clay fest. Oh, really?
Yeah. Yeah, go ahead. Yeah. Let's see if you can hear the question. Yeah.
Okay.
Hi. I just have a question regarding the 3D printing technologies used for the salts and the Chardonnay and the clay.
Mm-hmm.
It seems different from FDM based printing, but I'd like to know what it is.
Right. Yes. Okay. Yeah, I didn't explain that, but there are a number of 3D printing technologies that we're using, and all of the materials that we invented use a process called 3DP. In fact, it's really the original 3D printing, and the word 3D printing comes from that specific technology. It's just become an easy word for additive manufacturing, a more catchy word. But what it is it's a process that uses a dry powder in a bed and selectively sprays it with a liquid. That liquid is primarily water and alcohol. And so that's what's being used. So we can pulverize any kind of powder, place it in this bed, mix it with something that helps it stick together, and spray it with water, and out comes the object. So if it's cement, we're putting in cement and we're spraying it with water, which works nicely, or plasters, or salt, even crystallized with water. Sometimes we had to add some kind of glue, some kind of sticky stuff inside of it to help it stick together. But that's what it's called. And these printers that we have are actually 15 years old. It's not a new technology, nor are the machines new either. And they're not so easy to use. However, the company still makes them, and they now go under the name of 3D Systems, and they're powder-based 3D printers. And so you can find them. They still sell them. They're a bit pricey to buy them new, but I have always thought this is the most robust and interesting 3D printing process there is.
Any last questions? Well, Ron, thank you so much. I wanted to thank Bailey for putting this together and actually coming up with the idea to do the Zoom. So thank you very much, and Michael and Western New Mexico, and for everybody that came out tonight. Thanks again, Ron. Appreciate it.
I share that. Thanks. Thank you all.
How many 3D printers do you have?
Oh, at the height I had 38, but I don't have that many anymore. I'm paring down.
Well, if you need to unload a couple, you can send me a couple.
Okay, I don't think you want them. That's why I'm paring down.
Sounds good. Thanks a lot, Ron. I'll talk to you soon.
Okay. Thank you all so much. I really appreciate you accommodating me in this way.
Have a good night.
Good night.
Good night.
Good night.